Hello Year 12 chemists, welcome to TP's Chemistry Cuts. In this lesson, the water dissociation constant is introduced and then used in pH calculations involving bases.
We were looking at factors that will affect pH, and we started with the fact that if you take an acid or a base and dilute it, that will alter the pH, because the pH depends upon the concentration of H3O plus. And if we change the type of acid from a strong to a weak, or the base to a strong to a weak, that also affects pH. And we spent a large amount of that lesson actually going through what we meant by strong and weak acids and bases. Okay? And the first thing to say is that strong acids and bases are those that completely dissociate. That's the word that you should be using. Completely dissociate when you add them to water. Okay? And they give high concentrations of hydronium ions for acids, hydroxide ions for bases. And here are a couple of examples. And the all-important thing to note are these one-way arrows. Okay? There's no reverse reaction going on. Okay? Whereas if we look at weak acids and bases, again, the phrase we use is partially dissociate. Okay? And that means when they add it to water, you get low or relatively low concentrations of hydronium and hydroxide. Okay? And I've got these two examples up here, which I'm going to talk about next when we talk about amphiprotic species. And the all-important thing to note is these things are reversible reactions. And it's really, really important that you make that clear distinction. Strong acids and bases, one way, reversible for weak acids and bases. Now the interesting thing, if you look at these types of weak acids and bases, the sort of proportion that you're looking at, if you look at ethanoic acid, this is one of the stronger weak acids, and that's usually about 1 molecule in 100. Okay? There is nothing in between. You don't get sort of like a spectrum of acids and bases covering the whole range from weak to strong. They're either like this or they're like this. Nothing in between. Okay? If we look at these two, a weak base and a weak acid, okay, we've got the transfer of, and we'll do this, keep doing this because it's instructive to remind ourselves of why something's a base. The ammonia accepts a proton from water, and you form hydroxide as part of, as one of the products, and that's what makes the solution basic. Whereas for ethanoic acid, the transfer is in the opposite direction, where the H plus moves from the acid to water, and you form a hydronium ion, which makes the solution acidic. Now, so far, what we've looked at is you can calculate pH using this expression. And you're given that in the on a piece of supplementary supplementary data sheet, so you don't have to remember it. But to work out the pH, we need the concentration of H3O plus, and for an acid, that's all well and good. But what do we do with bases? Because there's no hydronium ion anywhere in that equation. So where do we get it from? And to answer that, we need to look at water in these two reactions and what it's doing. Okay. So if we quickly label this up as acids and bases, so this is a base because it accepts a proton, and this is what you've got to keep saying to in your mind's eye. This is accepting a proton, it's a proton acceptor, therefore it's a base. Whereas ethanoic acid in the second reaction is donating a proton to water, so it's an acid. Okay? And implicit in that is what's happening with water. In this case, water is donating a proton to the base, so that makes water an acid. And if we look at in the second example, water is accepting a proton from ethanoic acid, so that makes it a base. So the question we have to ask ourselves is, what is it, an acid or a base? And the answer is it depends. in this case, it's acting as an acid. In this case, it's acting as a base. And it depends on which reaction you're in. Okay? And substances that can do this, like water, are what we call amphiprotic species. Okay? So, amphiprotic can act as an acid or a base. And it depends on which reaction you're looking at. Water isn't the only one. There are others. Now, the interesting thing is, and I suspect one or two of you are already asking this, is if it can act as an acid in some instances and a base in other instances, what's it to stop itself acting as an acid towards itself or a base towards itself? Why can't one water molecule donate a proton to another water molecule? Because it's quite capable of doing that. And the answer is it does. That actually happens. So in water, pure water, that reaction occurs where one molecule of water acts as an acid and one molecule acts as a base. So the acid donates a proton to the other water molecule, which accepts it and acts as a base. Okay? So this is a reversible reaction. And it doesn't occur. So it doesn't occur to a great level, but it does actually happen. And so, if we say that this is the acid and this is the base, and the proton is transferred from this one to this one. Okay? Because the acid donates the proton to the base, and so what you end up with is OH minus plus H3O plus. Okay, is everybody happy with that? Okay, so if we just take away all acid and base is away from this and just have pure water, we're just looking at pure water for the moment, then there's no reason why one molecule of water can't act as an acid, another as a base, and the protons transfer between the two.
So you know when we're drinking water, have they just balanced each other out?
We'll come to that. We've just come into it. Now, when you see this, you think, oh my gosh, am I drinking something that's got an enormous amount of that and an enormous amount of that, and is it going to be dangerous? And the answer is no, because this only happens to a very, very small degree. And in fact, you'll see, when you see the number, you'll think, oh, that thing looks familiar. Okay. So this is a very, very small degree. So if we write this out in full, or more like a chemical equation, because I've tried to accentuate what's going on here by putting two separate water molecules, what we've got is H2O, and if we put in all the states properly, then we get OH minus and this has got an KC associated with it because it's a reversible reaction, and all reversible reactions reach equilibrium, and this one is no different, it will reach equilibrium. Then there's a KC. What's KC equal to? Now this is a little bit of maths, so this is going to be a little challenging for one or two people because we're going to talk about the significance of numbers. So if we look at water, 1 litre of water is approximately 55 moles. So the concentration of water is 55 moles per litre. In pure water, these two have the concentration of about 10 to the minus 7 moles per litre. That is a tiny, tiny number. I think in the last lesson I said it was something of the order of 100 million. In fact, it's only 10 million. So 1/10,000,000th of a mole. So what we're talking about, the difference in concentration is 8 or more orders of magnitude. That's an awful large difference. So if we start to change these, and this expression is just like any other reversible reaction, if we add in OH minus, then the reaction will be susceptible to readjusting itself. Okay, because Le Chatelier's principle applies just the same, and so they'll react together to try and remove them, etc., etc. When you do that, and you consider the relative concentrations of these compared to that, and don't forget it's a square as well, then any changes to this will have no significant effect on the concentration of water, because it's about 8 orders of magnitude greater. What you're doing is changing a concentration here, which will affect this one way down its number. Okay, so the significance in terms of the change to the absolute number is going to be negligible. So what we can do is we can assume, and it's a fair assumption, that this stays constant. It's a constant. So we can ignore it, because it's not changing up and down. It's not going to affect our equilibrium constant itself. It's only these two that actually change. Okay? Now if that's complicating you and it's sort of confusing you, just don't worry about it. Just take on board that if it's the solvent, we just leave it out. The reason, as I say, we leave it out is because anything that happens to these two will not significantly affect that concentration. Okay, so anything that are solvents, and in our case, the only solvent we're going to consider is water. So if you ever see water as part of the reaction, you just ignore it. Okay, in the case of, now that's a year 13 thing. This is the only example in year 12 where you will have this. Okay, so it's just this one reaction at the moment. So what we can do is, if this is constant, we can just put it up here and just merge it into the Kc value, because it's just a constant factor that just bumps the value up a bit. Yeah? So what this then is a very special version of Kc, and it has its own little letter. It's actually called Kw. Okay? Now, just as an aside here, so you know, this is still an equilibrium constant, okay? Which means that the value we quote depends on the temperature. The standard value, okay, is 1 times 10 to the minus 14. Oh, that sounds familiar, doesn't it? 14? We're talking about the pH scale. Yeah. See why it starts to slot into these peculiar numbers. Okay. 1 times 10 to the minus 14, but that is at 25 degrees C. And remember that as you change temperature, depending on which way is the exothermic and endothermic reaction, that value will change. So we just assume everything's at 25 degrees C. So we're not going to complicate matters with this. You can see the panic already coming in here. We're going to keep it at 25 degrees C. We'll assume everything we're going to be doing is at 25 degrees C. And this reaction here occurs in any aqueous solution. Any solution where you've got water as the solvent, this is happening in the background. And when you add acids and bases to the water, what you're in fact doing is just disturbing this equilibrium. And you just apply Le Chatelier's principle, if you like. And so by adding an acid, you're increasing this concentration, which means that the two of these react together to try and remove it and pull it back down again. And so it pushes things that way, but this concentration is still greater than that. Okay? It tells you that, and the reason I'm telling you this is that if you add a base, okay, so you have a massive amount of base to this, so you say have a 0.1 mole per litre solution of base, this is 10 to the minus 7. So it'll try and react away some of that, but there is only 10 to the minus 7 of that, so some of it will be reacted away, and it will pull the concentrations down again, so that Kw can go back to 10 to the minus 14. However, you will still have a tiny, tiny, tiny amount of H3O plus and a very much larger quantity of OH minus. The important thing is, though, we still have some H3O plus in the solution, even though it's a basic solution. And that's why we can measure a pH for it, because there's H3O plus there. If we got rid of it all, there would be no pH, because there'd be nothing to measure. We are measuring this concentration. Okay? So this is why this equation is so important. It tells us that whatever we do to this, there'll always be a little bit of this. It's just that it gets smaller and smaller and smaller to the point where it is tiny, tiny, tiny. But it's still significant because we can measure the pH. Yeah? So I'm going to put a little arrow from here to there.
Would you be able to clarify something?
Sorry?
What seems the parity of the protein is basic?
Just a minute. No, what I'll do, this is 55 mole per litre, yeah, in pure water. This would be 1 times 10 to the minus 7 mole per litre. This would be 1 times 10 to the minus 7 mole per litre, because this is pure water, there's nothing else there, so these two concentrations will be the same. There's nothing else there to affect it. So, under normal conditions, with no acid or base there, you've got equal quantities of these, equal concentrations, but they are tiny, really, really small. That's 1/10,000,000th of a mole per litre, whereas this is 55. So that's 8 orders and more of orders of magnitude greater. So, to all intents and purposes, there's nothing there in terms of significance related to this. If you add a base into this, Le Chatelier's principle applies, and so because it's at equilibrium, you've lost equilibrium. Okay, it was at equilibrium, you've added a base in, you've increased that concentration, so it's lost equilibrium. These two react together to try and pull it down, because you're trying to minimise the effect of the change. But because this is so tiny, it's got no chance. If you were to add 0.1 mole per litre, there's only 0.00001 mole per litre of this. It can pull it down as far as it can, and as it does so, this gets smaller and smaller, so this value gets smaller and smaller. It brings it back, KW, back to the value it should be. But it's telling you there's still going to be something there. It's tiny, 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 but it's still there. This will be a 0.1 also, because if the concentration of this relative to 0.1 is tiny, insignificant, so it'll bring it down, but it's still there. There's a tiny amount there. Okay? So no matter what you do to work an aqueous solution, you can bump this right up. You'll always have some OH minus there. Tiny, tiny, tiny. But what we're more interested in is if we push this right up, there's still going to be a tiny amount of H3O plus there, always, because of this equilibrium. Excuse me, I have to take this.
Did you do that on Monday? I got started by
Did you do all of it?
we could have gone to those on the side not to. Decided not to do that. How do you do that?
It's just that, you know, I have a disabled son. If it's something to do with him, I'd have to answer it. It was actually the dentist. It's a great excuse for not.
That 1 times 10 to the power negative 14 is if you've added lots of OH.
No, that's the value of K. That's the equilibrium constant for this reaction at room temperature. This is pretty much negligible. There's so little of this, so little of either of these two, that you couldn't do anything reacting with them. But the fact that you've got 10 to the minus 7 of this, if you do pH of that, calculate the pH of that, that's minus the log of the concentration, what's the answer? 7. Yeah, well, that's why we get neutral pH. That's neutral pH. What it's telling you is that's the concentration of that. We know that these two are the same concentration because they've been dissociated from here. So if you take 2 of those, you're going to get... So every 2 of those gives 1 of those and 1 of those.
Yeah,
So
how do we get negative 14?
That's been measured.
So yeah, but like, where does it come from?
That's been measured.
Yeah, but how? It's basic, right?
No, it's not basic. 1 times 10 to the minus 14 is the value of Kw. Kw is an equilibrium constant. It's not a pH scale. What it's telling you, that's a tiny number. What's that telling you? A small number tells you what for Kc? Go back to equilibrium. What does a small number for Kc tell you? It's a reactant favoured equilibrium. It's saying you it's massively over that way. There's some over this side, a tiny, tiny amount, but it's pushed right over that way. Yeah? So you've got to touch yourself away. This is not the pH scale. It relates to it because of that 14. So what you're doing is you're changing things from 10 to the minus 7 up and down, and that's why 7's in the middle, and you go up and down with the pH scale. Yeah?
Okay, that makes so much more sense.
Yeah. Okay, I'm sorry, I should have made that clear.
No, that's fine. That clears everything up.
Right then, so this writes, what I want to do, you will never be expected to explain this, but what's so important is you understand that everything you do with acids and bases are upsetting this equilibrium. But what you're dealing with here are such small numbers that you're not going to shift anything that way very much because the tiny numbers won't let you. Yeah? So 10 to the minus 7, if you put 0.1 mole per litre of this stuff in, this can only go down a little tiny, tiny amount and bring it down a tiny, tiny amount. But that means there's still some of this stuff left. And so there'll always be a pH value for it. Okay, because there's always some H3O+, because that's the one thing, very important thing. Because it's the pH scale. Okay, so what I'm trying to say is, regardless of what you do, you can overload it with OH minus in solution, because we've got an equilibrium involved in here. These will react together to try and remove it. There'll always be some H3O plus present. It'll be in a tiny amount, but it'll still be there, which means that we can still calculate a pH value, because pH depends upon the concentration of H3O plus. We're almost there. It's this thing now that we're going to use. This is a very accurately known, you'll be told this, that Kw is equal to this, and that's its value. Okay, we can actually use this now, and it's how we actually calculate the pH of a base. Okay. What we need to do is, if we know the concentration of OH minus, we need to be able to calculate the concentration of H3O plus, and then use that to calculate the pH. The beauty of this expression is, which I've written here, if I rearrange it, oh no, not rearranging, maths. We're going to rearrange this, so if we know this for a base, we know the base concentration, we can now calculate the concentration of H3O plus. Okay? H3O plus concentration is Kw divided by the concentration of OH minus. Okay, so that's the thing we want to calculate. These are the things we know. That's equal to 1 times 10 to the minus 14. And this is the known concentration of the base. The problem we've had is we know what its concentration is, but where do we get the pH from? Because it's all about OH minus and not about H3O plus. We need that concentration of H3O plus, which this tells us is always going to be there, but in tiny, tiny amounts. We know what the value of Kw is, so we can now calculate it. And it's given by this very simple expression. So I've tried to make this a really, really easy calculation, and then we'll start mixing it around a bit. Okay? So the first thing is that the concentration of H3O plus is equal to the Kw, which is 1 times 10 to the minus 14 over 0.1. Okay, notice I've used a sodium hydroxide solution, which means if I add 0.1 moles of sodium hydroxide to water, a litre of water, I'll get 0.1 mole per litre of OH minus, because it's a strong base. Okay? And I need to make it clear, this year you will only do calculations involving strong acids or strong bases, where you get complete dissociation. So the concentration you are given of the acid or the base is the concentration of H3O plus or OH minus. Okay? You are not expected to do anything with weak acids and bases. That's next year. Okay? So this that, okay, nice and simple, and then the pH is equal to minus the log of that surprisingly is 30. So what's the first thing I can do with that? Very first thing. Find the concentration of? Yes. So the concentration of H3O plus goes straight to your supplementary data sheet. If you can't remember it, just look at the equations and you'll see the right one. That's equal to 10 to the minus pH, which is equal to 10 to the minus 11.5. Can somebody calculate that for me?
16 times 10 to the power of negative 12.
Which is a very small number. But then, that's what you'd expect, because this is a base. And we're looking at the concentration of H3O minus. So this is basically 0.011 times, and then 316. So it's a tiny, tiny concentration. Not significant in terms of all the other concentrations, but it's significant because we can measure a pH from it. Okay, so the next thing is Kw is equal to the concentration of OH minus times H3O plus. Okay, we want this now. We know that. We know that. This needs to be the subject of our equation. So the concentration of OH minus is equal to Kw divided by the concentration of H3O plus. That's 1 times 10 to the minus 14, and it's divided by 3.16 times 10 to the minus 12. Use brackets. Use lots of brackets.
3.165 times 10 to the power of negative 3. Yeah.
I'm going to put that as 3.17, and we'll talk about significant
It would
figures
be
in the next.
3.16 if it's 2.
165. You said, didn't you? Oh, you waved it up.
Yeah.
3.16. Okay.
Yeah.
Okay. So that's the two types of calculations you'll do with bases, and analogous ones with acids. So you should be able to now calculate the pH of a solution given the concentration of base or acid. Okay. Or you should be able to do the reverse, given the concentration, given the pH, calculate the concentration.